Hello and welcome to the latest ADISA podcast. My name is Steve Mellings. I'm the founder of ADISA, and today I'm joined by Sebastien Farnaud from Coventry University. He's created what's called the Bioleaching Group at the university, and we're going to talk about bioleaching today. So welcome, Sebastien.
Thank you, Steve. Thank you very much for having me today. It's a pleasure.
For anybody who's unfamiliar with the term bioleaching, perhaps you can give us a little bit of layperson's description of what is bioleaching and what its relevance is for electronic waste.
Okay, so bioleaching is part of that big group of what we call a bioremediation, which in a way you use a living organism to remediate to some issues. So the bioleaching is particularly targeting metal. So what it is in a nutshell is using microorganisms, so mainly bacteria, a fungi to a bacteria, to actually metabolize or recuperate, extract metal. It's not something which is very new because, in fact, in the mining industry, they've been using it for decades. In fact, a long time ago, even the Roman and the Greek were using it, but they didn't know what they were using. But they were using those microorganisms to oxidize the metal and to recuperate the metal. So in the mining industry, you can imagine you've got those huge amount of rocks and they want to extract a minimal amount of ores. So they put that together, put some bacteria on it in a nutshell, and the bacteria do the oxidation of the metal, extract the metal, and that is up to us to recuperate those metal. So what we're doing now is try to adapt this method of using those bacteria to waste, and particularly to electronic waste, which is in fact a really good thing compared to if you think in the mining industry, they've got those tons and huge amount of rocks from which you have to extract little ores. In our case, you got those PCBs or electronic waste where the metal are concentrated, and from there we give that to feed to the bacteria, and the bacteria just get it out and have it.
It sounds futuristic to me. I know when we spoke about it and when Andrew from N2S explained this to me a few months ago now, I couldn't get my head around the concept. It does seem quite futuristic to me. You mentioned that it's a very old process. So this is a very real proposition. This isn't something which is academic and theorized. It is a real practice.
Isn't it paradoxical that something which is as old as the world is something that we find is completely futuristic? I mean, this is something that the bacteria I'm using, they're bacteria which have there for billions of years, and they've done the job for billions of years. In particular, so in bioleaching, you have different methods, but just to take the most representative one, what the bacteria do, they need iron to survive, to produce energy in a nutshell. So what they do, they find iron and they oxidize iron, ferrous to ferric iron. Then ferric iron, which is less stable, try to go back to ferrous, and it's ferric iron in itself which will oxidize other metals which are present. So for example, you got your bacteria growing on a bit of iron, and there's a bit of copper stuck in a rock. So what you'll do, the bacteria will start oxidizing iron because it needs iron to survive, and then in turn iron will oxidize copper, so copper gets released, extracted from solid form and back into the bacterial soup. That's as simple as that. And sometimes the most simplistic thing sounds the most futuristic. It sounds like Star Trek, but it's exactly that way.
It is Star Trek.
And I love it. It's great.
But I mean, we chatted last time about this, and I clearly I'm a dinosaur because I can't get my head around it. Really, it's what we're talking about in layperson's terms, and I'm going to keep it simple because that's the only way of me understanding it. Really, is that we're able to introduce living organisms, bacteria, to electronic waste, which those living organisms require certain metals. And those certain metals can therefore be extracted from the electronic waste via the organism. Is that, in layperson's terminology, what we're talking about?
That's exactly what it is. Now, the thing is, as I said, that's what bioleaching is. It's about oxidizing metal. So in a nutshell, to make it really general, bacteria do oxidize metal, which are in a solid form, so that when they get oxidized, they get released in the bacterial soup. Now, the way to do that, one of the main group is actually using iron or sulfur. So they oxidize the first component, which then in turn will target the metal. There are other one if a chemist is listening to us now, the first thing would be that, hang on a sec, if you look at what we call noble metal, like gold, platinum, palladium, those metals are much more difficult to be oxidized by iron or by sulfur. So what happened in this case, it's not these bacteria which really will do it, it's another group of bacteria that can themselves make some acids, for example, cyanide. So these are cyanogenic bacteria, and which is then that acid that will target the metal. So again, but altogether, what it is about, it's about creating a substance that will target the metal, which is solid. But once it got oxidized, it's extracted from the solid support.
And in terms of the range of metals that is possible to be recovered using this technique, is there a narrow range, or is it a broader range at present?
And this is the question everybody asks.
Yeah.
And the key is that, as far as I know, and as far as we've tried in the lab, and you see in the literature, I cannot see a metal which cannot be extracted. By definition, most of metal will be to be oxidized. It's about moving electrons around. So by definition, I can't see why metal wouldn't be able to be oxidized, whether they're very, very, very stable, like those dumbbell metal, or less stable. You need to find the right way to oxidize them. But as far as this, so we've been targeting all the base metal, like copper, zinc, lead, and all that. They're really easy to do. Then you go the most noble one, less reactive, noble, palladium, platinum, a bit more difficult, but again, there's another method to do it. And then, of course, people get interested. What about these rare earth metal, like erbium, all the tiny bit little one? And same again, methods have shown that, we've shown in the lab, and some of the group have shown that, yes, you can also oxidize them, you can bioleach them. So where we stand, there's not a single metal that we found so far we cannot bioleach.
And let's talk application of this. So clearly, one of your main sponsors is N2S Network to Supplies, and Andrew Gunmasel's explained this to me various times, actually. Slowly, I stressed so that I understood it. He sees a very real-world application for this, and clearly, I can see that as well. But without sort of taking away the grand scheme, where do you see bioleaching go where electronic waste is concerned? What's your vision for where this technique could go?
My vision is the one I use for my group. I tell them, look, this is quite simple. Whereas on one hand, you got a typical academics who tend to do little experiment in the lab, get a paper, and this is the end of it. And they tend to be academics, surprisingly maybe. They're a bit negative. Oh, that's just us having a hobby. I don't see it at all like this. And this is why we already went so fast. I see within the next 5, 10 years, 20 years, I can see a big plant in every city in the world where people will bring their waste and the electronic waste and the metal waste, which will be recycled exactly this way. I really can see this as a true method that can actually be implemented. It will require some investment, some change in culture, but it will happen. There's no doubt about it.
And let's talk the practical side in terms of a bioleaching. I was going to use a very British word, tip. So a refuse centre for bioleaching. What size is your lab in terms of capacity? So if we had a PC, for example, and the process of breaking it down into components and applying the right type of organisms to each, can we scale this process? That's
the ultimate point. That's a very good question. So I always use the mining industry as an example, because if you go to Chile or Colombia, you got those open mines which are miles long with those hundreds of meters high incubators. So this is really, really big. So what it shows the feasibility. But when we talk about utilizing secondary source, we're talking about smaller amounts. Instead of needing tons of rocks to get a few milligrams of gold or aluminium, we're going to use kilograms of PCBs. Now, the trick is that it's all about the size of what you feed your bugs with. If you think, first of all, PCBs are much smaller than those tons of rocks, then I think the key is going to be to combine mechanical extraction with the bioleaching. If you start with a PCB, so a few kilograms, you'll have big PCBs. What you're targeting is within the chips, within the gold fingers, within all the other elements. So the key is that once you taken them out of the PCB, then the size is much, much smaller. Then if you decide whether you decide or not, and again, that's becoming technical, but if you want to shred these, or if you want to part of these, or put them in a ball mill to make it smaller, you're ending up with quite a large amount of metal in quite a small amount in a small container. So somehow, when we're going to start talking about those 50 million tons of electronic waste generated every year, we're talking about a lot of material that can be taken off before you actually end up with what you want to target with your bioleaching. Saying that, it still means that from the lab, from the bench lab, from a flask, we need to still upscale this. And this is exactly what we've done in a very short time with N2S. N2S is a company with 50 years has been working with recycling electronics, but they didn't have any knowledge of the microbiology part of it. So what we did as part of that 3 years grant, we proposed that we're going to build a lab on site, which is what we did. So within the premises, then we're going to have 2 labs, which have got the facilities to extract already some of the metal, which are already commercial application. So when you need we need to have an incubator with few flasks to start with. Then we build some sort of tables. We've included some bioreactors, but this is a relatively small amount to already process quite a large amount of elements. Now the key is going to be I was talking recently to some battery recyclers, because what I really want to target to are going to be now these electric vehicle batteries with the lithium, the cobalt, the manganese, and so on. That's a fantastic target. And it is a place where we do not face yet those millions of tons of waste in front of us. So from the beginning, if we decide how to target it with the provider and the manufacturers, this is what it's about. So instead of having those massive amount, and the battery recycler told me, what do I do? Do I take my battery, throw it in your bugs, and they're going to deal with it? Ideally, that's what we want. And I'm not sure that one day we won't be doing it. That might be the ultimate thing. But I think this will be feasible when whatever we dump in is ready to be accessible by the bacteria. They're not very fussy. They get in. They'll find a way to get in. We're talking really, really small bugs there. But the key is that if somehow the manufacturers start manufacture their bits so that in mind, they already know what a recycling is going to be, then we're going to facilitate that. So instead of starting with, now we're talking of recycling material from the 70s, 80s, 90s, which are completely out of it. So those big, large boards, some of them completely covered with gold. What do we do with it? So now we need to be inventive in thinking, how can this be reduced into being dealt with by the bugs? Now, if we start thinking the other way, if we got now the manufacturers of tomorrow telling us, right, so what you want to do is not hydrometallurgy, is not pyrometallurgy. What you want to do is feed these into some containers for bacteria. And then we deal with them. Well, they're different kind of containers. They're different kind of medium culture. They're different kind of what to do with. It could be a table. It could be a flask. It could be a bioreactor. But tell me what it is you can adapt to making a battery, making a PCB. And this is where we are. So the upscaling, if you're talking within the next 5, 10, 20 years, we're not talking just to dealing with the old bits. We're talking about not having to constantly facing a waste and an issue with the waste. We'll be talking about part of what we really call the circular economy, where what I'm dealing with has been thought by the manufacturers and providers. They will build things that I'll fit into my bugs. So then somehow, instead of having, like in the mining industry, tons of rocks to extract tiny bit of milligrams, we're talking about something which is easily scalable.
And this is interesting, Sebastien, because the circular economy, which you talked about and sustainable IT, a lot of the trigger points for extending product life cycles, so right to repair, etc. A lot of the issues are faced because of the manufacturing process and the design process. And so what we're saying is not only is there a issue with extending the product life cycle because of the way it's being designed and manufactured, even the way that we recover material at the moment is being challenged. If the design of the device in the first place and the way that the devices were constructed had an idea of your end point for recovery, it would make the recovery process much easier. Is that the same premise?
So it will make it easier, but if you think about it, the key is for the time being, I'm an academic, so I'm not a businessman, and people tend to think that, easy for him to talk. He doesn't realize he's talking about a business which has been there for decades, and he want to change the whole thing. I'm thinking that here again, if we start recovering all these material which can be then recycled, if we start preventing or facing all the new policy by DEFRA, which is really putting on that more and more now, the manufacturer will have to guarantee that whatever they manufacture can be recycled. All this, if we remain as we are, is going to come to what sort of cost? If somehow we try to change infrastructure so that the recycling is really easy to do, there's even a gain of cost. It's not actually what terrifies businesses is that those guys want that innovation is going to break completely what we've done. It's a change in infrastructure. It's requiring a massive investment. I believe that, again, if you look at it in the longer run, we're talking getting cost, because it will actually be exactly what it is. I can imagine that also those manufacturers will actually want to be working with the recyclers because they will get the material back. So a cut in cost on the material too.
I mean, I find this fascinating. It's completely alien to me, no pun intended on the futuristic piece, but for me, it's just a really groundbreaking initiative of using an old technique, which I find staggering, and repurposing it into a real world problem, because e-waste is a massive, massive challenge. What do you need, Sebastien, from your perspective heading up this project? What do you need from from the industry, from the manufacturers, to help you evolve bioleaching into a real world solution?
So I think when you talk to academics, it's always, we need funding, and it's true. We need funding to show the evidence. But I think it goes beyond that. It will go that just asking for funding, again, because I'm thinking business, I think I'm asking for more. I'm asking people like you, people to raise awareness that it exists and that it's feasible. It's not just a fancy thing. It's feasible, and it's bound to be not only feasible, it's bound to be much better at all level. To start with, it's going to be better because what we're doing is something which is, first of all, environmentally friendly. So we don't have this huge carbon footprint, using toxic material, high level of energy. We don't have that. We also have, economically, the growing those bugs, apart from investment in infrastructure, growing the bacteria is extremely cheap. That's a really good way. Economically, this is important. Where we stand so far, the UK doesn't have all the facilities to extract all the material. And in a lot of instances, these PCB, most of bits the bits we can take them out of PCB, but still we end up with massive containers full of material. Most people don't even know what the content is. This is sent abroad, Asia, anywhere else, and then those guys deal with it, come back and tell those companies, great, we've been extracting that much of palladium, that much of gold, here it is, thank you. So not only we don't know what was lost, we lost the material at a very high cost, because we're paying to lose something. What we're providing is something in situ, inside, we're doing here. So the project or the bioleaching start earlier. We're starting by, first of all, thinking, look, you want me to extract some material, but what is it you want me to extract? And I find that most of companies would say, well, I'm not too sure what is on that PCB, because that has involved many different companies creating many little chips and little elements on a board. You realize that nobody's got a full content. So what we start by doing is that through different technique, mainly through ICP, we can actually analyze. We get a material, we put in acid to destroy it completely, and then we analyze all the elements. So then we come back with a list and feel like, did you know that in that PCB you had all this material? And then people get completely amazed. And then now we know what we have. We know how we're going to design specific method that goes from the bacteria to extract it down to the selective way we will actually recuperate it to then be able to send it to an application. And this is quite important. If you look at most of method nowadays in hydrometallurgy, fair enough, you just melt the whole thing, you burn what you don't want, and you recuperate what you want. Most of the time, you end up with something which is not very pure. What we're proposing is that, depending what you want to do with it, we will elaborate different methods. The one we published recently to illustrate this was an easy one. We decided, right, you've got a high content of copper, so we're going to show from those bit of PCBs, we bioleach the copper, all the copper comes solution, and then from that solution there, what do you do with it? And that's a big question. A lot of academics have done that. You've got a lot of papers showing that, great, got the material, it's now in my soup, great, publish a paper, end of it. But that's not really circular yet. So what we've done then with engineering, we combine new techniques. In this case, it was electrowinning, where you actually put your solution in an electric field with your cathode and your anodes, and then with the electric current, you selectively extract the copper to create a foil of copper. So in the end, what we do, we start from PCB, and we end up with a 99.9% pure foil of copper, which if you want, you can straightly recycle into a PCB. That's what you want. But the wealth of it is that you can use it for anything. So if some industry did not require 99% purity. At a different stage, we can do even a quicker, cheaper method to get some sort of alloy for the application. And this is what the key is. We're not only proposing to get a better way to deal with your rubbish, we're dealing with it so that it can be reused. So many people talk about circular economy, but you look at it, there's always a missing link in the end. So where do you go next? And that's, well, somebody else will deal with it. But that's what we do. We want the people to build it to know already that whenever we'll deal with it, we know which other market, which other part of canvas that's going to be addressed to. And this is important.
Yeah, agreed. And I agree on the missing link within circularity. There is always that missing link with the whole concept. I think this is phenomenal, Sebastien. I'm aware of time. So I'm going to suggest that we close this one off, but I would very much like to do a follow-up with you and possibly do a piece where we actually might see parts of this process to make it seem real. I know we talked about post-COVID, coming back to my old university. When you were talking about growing bacteria was very easy. You clearly came to my student house when I was living in Coventry. We had quite a lot of bacteria growing around there, I can assure you. It's like most student houses do. I'm going to say thank you very much. I would really like to do the follow-up. I think
I hope you will. You need to see that. You need to show it. We can literally really show you. So this is your PCB. That's where you fit it. The bacteria will work on it for several days, but already then on a bioreactor. And that's the key to more. We can work either in batch or we can work in continuous method. So I've got in my head, you're talking about vision. I've got those plants in mind where people will come and feed the bacteria. The bacteria will actually extract those metals, and then on different outputs and outlets, you can have different methods, whether it's ion exchange, electrowinning, and then you end up with you'll see your foil there, or the sponge with the metal you want, and this is there. So we've got a setup. You have to come. You need to record that and show that to them.
I want to do. Well, I do want to do that, Sebastien, because I think this is fantastic. From I'm a data protection guy, and I pay a lot of lip service to the waste and material reclamation piece. When this was disclosed to me earlier on this year, I said, "Oh, okay, it's going to be in Petri dishes. It's going to be on a micro scale." But clearly, we've talked previously, and what you've disclosed today is it isn't that. It's something which is very real and scalable. And the challenge that you have is clearly funding time, which is like a lot of initiatives.
And I think the funding will come because the money is there. But it's true that people will put the money where they can get something out of it. So once we start with this awareness and showing that it is working, it is there for all the good reasons. I mean, that's why DEFRA loves it, because suddenly you got not only, it's a classic where people look at recycling where it's about getting rid of rubbish. But the way you do it is as important as the rubbish itself. Is to get rid of it by creating another catastrophe. There's no point. It has to be making sure you do that in a very green way, in a very safe way, in the best way, cost efficient, closing the cycle. You need to record us. You need to come to the lab and have a look at that.
Sebastien, I am definitely going to do that, sir. What I'm going to say is thank you very much for today's session as an introduction, and I think this will whet an awful lot of people's appetite for a follow-up. And I'll reach out to the guys at N2S as well, because I think it'd be really interesting to get them involved and talk about the commercial application of this as well, because I think that's really
a good place to see to going to their premises. I know quite a few companies. They go there and they really love it. So you could really have a look at how industrially it's not just in a lab, in academic, in a research lab. It's in application. So yes, it would be great.
Fantastic. Jolly good, sir. Thank you so much for your time. We're going to put up some contact details after this for people who want to know a little bit more and where they can go to do their own research for this as well. So there'll be some notes on there. Thank you very much indeed for your time this morning, Sebastien. I hope life in Coventry is still as much fun as it was when I was there.
It is.
So best wishes. Thank you very much.